Luminosity of a collider may be expressed in terms of the parameters of beams that collide at an intersecting point. There is a commonly known equation which, by its structure, is similar to the formula for luminosity of interaction with a fixed target. But instead of target density, the density of the intersecting beam is taken into account. Luminosity is proportional to the number of colliding bunches times the bunch intensity to the power of 2, also referred to as the bunch revolution frequency, divided by the approximate area of the beam. The beam area is calculated in terms of the root mean square of emittance, which is characteristic of phase volume and beta function at the intersection point. Beta function is a parameter that defines the size of a beam at a given point. If one looks at this equation without analyzing the real capabilities of an accelerator facility, one may conclude that it would be possible to generate infinite luminosity. For instance, it would be possible to increase the number of bunches circulating in the accelerator. It would also be possible to raise the intensity of every bunch. It would be possible to lower emittance, to decrease beta function at the intersection point, and thereby achieve the needed luminosity. Such a plain look at the equation very often leads to unjustifiable mistakes. For example, despite the fact that the circumference may be large, the number of the bunches in a collider is always limited. For a detector to work normally, one needs to avoid parasitic collisions inside the detector, and hence, the distance between the colliding bunches has to be larger than the longitude of the detector. The number of particles in a bunch may, essentially, be increased if the capacity of the injection chain allows it. A decrease of beta functions at the intersection point is limited by the capability of the magnetic system. And one can understand how low beam emittance may be if limitations are considered. The main limitations of luminosity are related to particle repulsion. In every accelerated and colliding bunch, there are particles of the same charge, and we want to obtain the minimum size of such an object that has a relatively high electric charge. After the emergence of the first propositions of colliding beam experiments, the main objection was the following. In a particle bunch, one couldn't achieve the density compared with the density of a solid substance simply because the bunch consists of charged particles. And particle repulsion won't permit the required density. The parameter which describes the actions of a space charge is a frequency shift of betatron particle oscillations in an accelerator. There are two sources of a frequency shift of betatron oscillations in a collider. The first one, which is general for any accelerator, is the shift due to the impact of the bunch field on oscillations of each particle located in this bunch. A bunch field is repulsive and electric, and it leads to a decrease in frequency, acting as an additional defocusing lens and results in a lower frequency of betatron or transverse oscillations. The second source of a frequency shift, common only to colliders, is the impact of the particle bunch made by the intersecting bunch at the intersection point, or at the collision point. In this case, the field of the colliding bunch acts as a strong defocusing lens, whereby being nonlinear. The linear part of the frequency shift is called the beam-beam parameter, due to actions of the colliding bunch. Here I have the equations to calculate the frequency shift driven by these effects. Why is the frequency shift crucial for the operation of any accelerator facility of the synchrotron type, or any other cyclic accelerators? A particle travels multiple times along the same circumference, and if, all of a sudden, the oscillation frequency coincides with the revolution frequency of the particle, or it is divisible by it, then the particle is affected by the structure's error, always in the same phase, and a parametric resonance occurs. Indeed, there are a lot more resonances in a magnetic structure than merely parametric ones. A general expression for a resonant buildup of oscillations is derived by multiplying an integer by the horizontal oscillation frequency plus another integer times the vertical oscillations frequency equal to an integer. If this condition is fulfilled, then the radial particle motion becomes unstable. All these resonances may be sketched in a special diagram called an accelerator resonance diagram. In this diagram, on one axis, there is the horizontal oscillations frequency. On the other axis, the vertical oscillations frequency, while lines are used to indicate those frequency values that satisfy the resonance condition. Integers, which betatron frequencies are multiplied by, define the resonance order. As an example, here you can see the resonance diagram for the Nika collider up to the 7th order. The strongest resonances have the lowest order. The 7th order is a rather weak one. But if we speak about a storage ring or a collider, we need to take into account even the resonances of a very high level, which might lead to the destruction of particles. The Nika collider is planned to have 2 operation points. An operation point is a set of 2 numbers, horizontal and vertical oscillation frequencies. The first operation point is located slightly lower than the half-integer resonance. The second one is a bit higher than the integer resonance. The area with no intersecting lines, which define resonance, turns out to be limited for either choice of an operation point. The maximum betatron frequency shift leading to a resonance and the destruction of particles may lie in the range from 0.05 to 1/10, depending on the choice of the operation point. To illustrate what I mean, I can show you the measurement results at the Tevatron collider. This is a resonance diagram, where dots are used to indicate oscillation frequencies of separate particles. The yellow color is used to highlight anti-proton oscillations, while blue is used for proton oscillations. One can see that different bunches have particle dispersions based on the oscillation frequency. Each bunch leaves its footprint in the resonance diagram. Depending on which order resonances are intersected by this footprint, the bunch footprint, the lifespan of the bunch varies. Accordingly, the Tevatron's operation point has been selected around the same area as the operation point of the Nika collider. The maximum shift of betatron oscillation frequencies is also around the 0.05. When dealing with such limitations, we may take another look at the equations for the beam parameter and the incoherent frequency shift due to the actions of the bunch field. These equations show different dependencies on energy. The particle frequency shift, due to the impact of the bunch field, slowly dies out with the increase in particle energy. Why does that happen? Besides the electric field, when particles move, a particle bunch also creates a magnetic field. The electric field pushes particles apart, while the magnetic field compensates for this repulsion. With high energies, a frequency shift due to the impact of the bunch field is usually negligible. For instance, at the Tevatron collider, the frequency shift as a result of the intrinsic field is 2 orders of magnitude lower than the frequency shift due to the interaction with the oncoming beam. When interacting with the intersecting bunch, the situation is reversed. The electric field of an intersecting bunch acts in a pushing apart way, and the magnetic field also acts in a pushing apart way. Therefore, for a high-energy collider, the main factor that limits luminosity is the frequency shift due to its interaction with an intersecting bunch, or the so-called beam parameter, whereas for low-energy colliders, and it is, in fact, being implemented at the Nika Collider for the first time, the dominant effect is the frequency shift due to the behavior of the bunch itself.